Hello, everyone. Welcome to the HPL seminar this week. Today, I would like to introduce our speaker, Pratham Singh. Pratham started his undergraduate at the University of Guelph in 2012 and achieved 2 bachelor's degrees in 2017. One is in biomedical engineering and the other one's in business administration. During his undergraduate, he also had a research project which was about a biomechanical assessment of judo skills. In addition, he worked for multiple companies, including Gates and Biomechanics Lab at the University of Guelph, Niagara Prosthetics and Orthotics Corporation, and Tampa Bay Rays, where he worked on various biomechanical research projects. Last year, he started his master's course at the University of Calgary in biomedical engineering under the supervision of Dr. Darren Stefanishin. Pratham is planning to do his thesis defense at the end of this year, and one of the future plans that he has is to work alongside the professional athletes to help them stay injury-free. For some interesting facts about Pratham, he has a level 2 coaching certificates from the National Coaching Certification Program, or NCCP, and also has a 3rd degree black belt in judo. He said he started his own judo club on campus, so I guess whoever wants to learn judo, Pratham could give some help. Today, we will be hearing about part of his master's project entitled as Making Stride on Ultrawide Bandwidth Technology, Determining Speed and Stride Length Using a Local Positioning System. Pratham, whenever you're ready.
Awesome. Thank you, Sangwon, for that lovely introduction. Thank you, everyone, for coming to my presentation titled Making Strides on Ultrawide Bandwidth Technology, Determining Speed and Stride Length Using a Local Positioning System. So let's get started. Here we have the 2018-2019 NBA champions, the Toronto Raptors. And when we were all following their historic run last year, there was a term being thrown around by the sports scientists, and that was load management. Now, what exactly is load management? Well, it's exactly like it sounds. You're managing a load, whether it be from urban development to electrical engineering. For sports scientists, load management is profiling an external load, i.e. the physical demands of the sport, whether it be during practice or match play. Now, there needs to be a balance between the demands of the sport and letting the athlete perform at an elite level. To avoid being overworked, it is essential that exercises are prescribed and detailed appropriately. For runners, it is especially important to detail position and speed data. For example, in a 100-meter race, achieving peak velocity is strongly correlated to race performance. Profiling additional biomechanical data, such as stride length, is also beneficial. For example, when comparing regional level middle distance runners to world-class level middle distance runners, regional level runners have a reduced stride frequency and a reduced stride length, suggesting a reduced peak velocity because speed is the product of stride length and stride frequency. Now, there are many modalities to profile external load. One such modality includes wearable technology. Previously, expensive lab equipment was needed to obtain accurate information. Video data typically required post-race analysis as well. Therefore, wearable sensors are now allowing runners to measure performance more typical of their gait pattern and have minimal constraints on the runner. One example of a wearable technology includes a global positioning system, or a GPS-based wearable. Unfortunately, a GPS-based wearable is not feasible for indoor applications because of tall buildings, weather patterns, etc., that may interfere with the signal. Furthermore, 75% of runners use a GPS-based watch, which typically only have a sampling rate of 1 Hz. And GPS data doesn't get better beyond 10 Hz. Another example of a wearable technology includes inertial measurement unit, or an IMU-based wearable. An IMU is extremely sensitive to drift errors, i.e. an offset in the accelerometer signal output. As the accelerometer data is integrated twice to determine position, the error in position will grow quadratically over time. As a result, an IMU is not very good at determining position on its own, especially over long periods of time. So an alternative may include a local positioning system or an LPS-based wearable. Now, what exactly is an LPS? Well, it's very much like a GPS in that it contains a satellite and a sensor. The satellite sends out a communication signal, the sensor receives it, and then the satellite stores that data. But unlike a GPS, the satellite hub is in close proximity to the user and not thousands of kilometers away. Therefore, an LPS is beneficial in that it can be used both indoors and outdoors. Examples of an LPS include Wi-Fi, traditional and infrared imaging, radio frequency, and ultra-wide bandwidth. Now, each of these examples have their own pros and cons depending on the application. For running, ultra-wide bandwidth may be the most beneficial because it covers a large frequency spectrum, yet consumes very little energy. Unfortunately, an LPS is not very good at determining gait events such as heel strike and step count. This is where the concept of sensor fusion may be very beneficial. Sensor fusion is the combination of inputs from multiple sensors into a single output. Sensor fusion could therefore characterize the gait event and position data. For example, the IMU would determine ipsilateral heel strikes, i.e. a stride, and then the LPS would determine position during the stride to obtain a stride length. Therefore, the purpose of my project was to compare speed and stride length from an ultra-wide bandwidth local positioning system equipped with an IMU to a video motion capture system, i.e. the gold standard. So I recruited 90 participants for this project, and once the participant came into the lab, they performed a self-selected walking speed. A self-selected walking speed that was a little bit slower, and then a self-selected walking speed that was a little bit faster. The participant then went on to do the same thing with running and sprinting. So this was the setup of the lab. There were 8 motion capture cameras surrounding a 10-meter running lane, while the LPS satellite hub was placed on a tripod positioned 2 meters behind the starting position of the participant. There were also timing gates placed at the 8 and 10-meter mark. The LPS, sampling at a frequency of 100 Hz, consisted of a satellite hub on the left that was in constant communication with the sensor in the middle, which was placed in a belt on the right that wrapped around the participant. As a result, the sensor was placed over the sacrum. It should also be noted that the IMU was integrated into the sensor. Speed and stride length from the LPS was obtained in the following manner. Speed from the LPS was obtained by finding the difference in radio frequency waves distance, much like a Doppler effect. Stride segmentation from the LPS was obtained by finding peaks in the superior-inferior direction of the IMU, as shown by the triangles in the figure below, and then taking the difference in position from the LPS position data. Speed and stride length from MOCAP was obtained in the following manner. Speed was calculated by finding the change in the sacrum marker's anterior-posterior position, and stride length was obtained by finding the anterior-posterior position between consecutive ipsilateral vertical position minima of a heel marker. It should be noted that the maximum speed and stride length during the last stride was analyzed for this project. Vicon Nexus and MATLAB were used to filter, process, and analyze the data. A low-pass filter of 50 Hz, i.e. the Nyquist frequency, was used to process the IMU acceleration signal. Bland Altman plots were created to compare speed and stride length in Microsoft Excel. Before we get to the Bland Altman plots, it should be noted that the local coordinate system, i.e. the coordinate system from the LPS, was aligned using autocorrelation techniques and then reoriented to the global coordinate system, i.e. the coordinate system from MOCAP, using a rotational matrix. This can be observed in the figure below, going from the LPS raw data to the LPS that's aligned and rotated. So those of you who aren't aware of a Bland Altman plot, a Bland Altman plot is a great tool to use when comparing a system to another system that's considered to be a gold standard. For this project, on the y-axis, we have the difference between MOCAP and LPS, which is MOCAP minus LPS, and the mean of the MOCAP and LPS on the x-axis. The red solid line is called the bias line, while the red dashed lines are considered the limits of agreement, which are 1.96 standard deviations away from the bias line. Now, in a perfect world, we would want to see the bias line intersecting the 0 mark on the y-axis, meaning that there's no difference between MOCAP and LPS. So looking at the Bland Altman plots for speed in all the trials, walking trials, running trials, and sprinting trials, for the most part, the bias line does get very close to the 0 mark on the y-axis. However, a lot of the data points aren't very close to this bias line, suggesting that there is great variability in this data set. Some key results also corroborate with this finding. When looking at all the trials, they're very close to the bias line being close to intersecting the 0 mark on the y-axis, and most of the trials being within the limits of agreement. However, the limits of agreement are quite far apart, suggesting that there's great variability in this data set. Looking at the Bland Altman plots for stride length for all trials, walking trials, running trials, and sprinting trials, we see very similar findings. where the bias line, for the most part, is very close to intersecting the 0 mark on the y-axis, suggesting that there's a little difference between MOCAP and LPS. However, the data points quite a few of the data points are far apart from this bias line, suggesting that there's quite a large variability. Some key results also corroborate with this finding, where for the most part, the bias line is close to intersecting with the 0 mark on the y-axis, and most of the trials being within the limits of agreement. However, the limits of agreement are quite far apart, suggesting there is great variability. So what are some key takeaways from these results? Well, the blended Altman plots suggest that this particular LPS may not be a valid method without further processing. This large variability between the LPS and MOCAP may be due to interference. For example, because the ultra-wide bandwidth covers such a large frequency spectrum, it might be picking up frequencies from things such as the wall outlets, the lights, etc. As a result, there was quite a large variability. So this might be reduced in an outdoor setting. Furthermore, when considering this particular LPS, the variability should be taken into account because even small differences can be detrimental in determining performance. For example, for older athletes, gait speed is a great predictor of performance. Being just a few tenths of a meters of a second difference can lead to statistically significant different outcomes. While for younger athletes, the max speed achieved is strongly correlated to soccer talent identification. So differences of just tenths of a meters of a second can lead to misidentifying elite soccer talent. Furthermore, it was interesting to see, though, that the bias and limits of agreement were reduced in walking and running trials in comparison to the sprinting trials. This may be due to a low sampling frequency, i.e. just not enough data coming in during those sprinting trials. So if users are wary of this variability, they may be able to use this particular LPS for walking and running trials. Furthermore, the LPS and sensor fusion may not have matched up to the MOCAP due to a reduced number of LPS hubs. For example, there is a system out there that uses 18 LPS hubs. Future research should explore the minimum number of LPS hubs required to obtain accurate information while not taking valuable time away from the athlete. Now, considering the limitations of this project, one could possibly include having a low sampling rate. Having a low sampling rate could have pulled the limits of agreement further apart, falsely suggesting that there was great variability. Future work should explore the reliability of an LPS and seeing if this variability changes between days, trials, and participants. Future work should also explore the resolution of the LPS. For example, even though there was great variability in looking at the max instantaneous speed, the variability may be reduced, for example, across 2 meters and obtaining an average speed that is then compared to timing gates, a system that many still consider to be a gold standard. Furthermore, pertinent features from a gate cycle that can better extract speed and stride length should also be explored. And that's exactly what I did, using machine learning algorithms. Now, machine learning is a set of algorithms that allows a system to learn patterns from a data set. And machine learning algorithms can also be applied to test future data sets. So the idea was that machine learning may recognize patterns that reoccur in the sensor position data. So I used 27 different waveform characteristics that have been proven to characterize and identify gait in previous research and inputted them into a stepwise linear regression model. These waveform characteristics included the RMS of position, velocity, acceleration in the x, y, z direction, the minima of the position, velocity, acceleration in the x, y, z direction, and the maxima of the position, velocity, acceleration in the x, y, z direction. Once these features were obtained from stepwise linear regression model, I was then going to put them into an artificial neural network and compare their accuracies. Conventionally, 80% of the strides were defined as the stride length obtained from the MOCAP, while 20% was used as the test data. It should also be noted that the models were cross-correlated across 10 different iterations. So looking at the mean square error of the stepwise linear regression across all 10 iterations, you can see that they are quite high. However, the best performing iteration was the 7th one, achieving a mean square error of 2.78 meters squared. And the model that was pulled from the 7th iteration shows that out of the 27 waveform characteristics used, 7 terms were deemed pertinent, while 6 of these were interaction terms, or terms that are multiplied with one another. So using these 7 terms, I inputted them into a feedforward neural network and observed the mean square error achieved during all 10 iterations. As you can see, this was substantially lower than the ones achieved from the stepwise linear regression models. In the feedforward neural network, the best performing iteration was the second one, achieving a mean square error of 3.62 times 10 to the negative 2 meters squared. The performance during this second iteration is also interesting to see in that the feedforward neural network gradually converged to a minima of 3.62 times 10 to the negative 2 meters squared. So looking at the Bland-Altman plots, comparing the stride length from MOCAP and the stride length that was estimated from the machine learning algorithms of all trials, walking trials, running trials, and sprinting trials, the bias line virtually intersects with that 0 mark on the y-axis, indicating that there's virtually no difference between the MOCAP and the estimated stride length from the machine learning algorithms. Furthermore, a lot more of the data points are surrounding that bias line, suggesting that there is reduced variability. Some of these key results also corroborate with this finding, where the bias line virtually intersects the 0 mark on the y-axis for practically all the trials, and most of the trials fall within the limits of agreement, and the limits of agreement are closer together, suggesting reduced variability. So what are some key takeaways from these results? Well, using a linear model into a neural network proved to be quite successful in estimating stride length. The relationship between the waveform characteristics and stride length was proven to be nonlinear. Furthermore, it was interesting to see that the mean square error was quite large when the neural network was less than 30 epochs, but then gradually converged to a minima of 3.62 times 10 to the negative 2 meters squared. Next steps should explore participants that can achieve even greater speeds or perform a cut or gate along a curved lane, and then seeing if the neural network can estimate a stride length under these two conditions. So what does this all mean? Well, for the industry, I believe that there's still a market for a LPS that operates in the ultra-wide bandwidth without having to do further processing. For the user, coaches and athletes should be wary of the great variability. Coaches shouldn't have to prescribe training regimes for athletes where they're having their athletes train on things that don't need training. For sports scientists, they should be wary of this variability when they're profiling their athletes' external load, because we all know the importance of load management. I'd like to thank the research team for helping me with this project along with the supervisory committee. This project was funded by the NSERC Alexander Graham Bell Scholarship, the NSERC Create WeTrack Grant, and the MyTax Accelerate Grant. The LPS was provided by Excotech Inc., a startup out of Penticton, British Columbia. Thank you, and I'll take any questions you may have now.
Thank you, Pratham, for the great talk. I really enjoyed it. If you have any questions to Pratham, please use raise a hand button at the bottom of your screen, or even just quickly shake your hands in front of your cameras, then I'll call on you when it's your turn. Does anyone have any questions to Pratham? Actually, let me go first. So you briefly explained about the kind of significance of these projects. So I'm just curious about, would there be any like future studies that you are planning to do in addition to what you have for now, or?
Yeah, so right now I am planning on seeing if the variability reduces for the average speed across the last 2 meters, and comparing it between MOCAP and also the timing gates.
See, interesting. Thank you. Art, I see you raise your hands. Please go ahead.
Yeah. My question is about how, so I don't really know how ultra wideband works, but I'm just wondering, is there anything about the basically its mechanism that explains why you would get less accuracy at higher speeds? Or also, are there certain directions that it's less accurate in? You know, like if you are moving directly towards that that hub, I could imagine that that's less accurate than if you're moving across it. And I'm just wondering, are there sort of things about the mechanism that that tell you expectations of how or where it should be accurate?
Yeah, certainly. So it's interesting that you point that out, because ultra-wide bandwidth, the signals coming from the ultra-wide bandwidth do get interfered with when using liquid materials. And so considering that people are liquid materials, if you're running towards the hub, that data will be very scrambled. It's a lot like using Bluetooth, where the Bluetooth just has difficulty penetrating humans. So in terms of where to position the LPS hub, ideally it should be in direct view with the sensor. So running across it, it would definitely be a little bit more accurate, but the best way to get data is if it's bore sight or directly in line. Does that?
And how about speed? So you had less accuracy at higher speeds?
Yeah. There's nothing that I could find in literature suggesting with speeds, but looking at the data, I'm just seeing that there just wasn't enough data coming in. So perhaps maybe at a higher sampling frequency, more data could be coming in, and as a result, the data set could be a little bit more accurate.
Okay, I think I saw Benno. You raise your hand if you have questions.
Yeah, I would like to make a comment first. It was very nicely presented. I enjoyed it, and congratulations for that.
Thank you.
You're welcome. The question I have is, what else than stride length and stride frequency can you determine with this method? You know, I mean, typically when we do full body analysis with kinematics and kinetics, we are interested in questions like loading of the knee joint on the medial side, or I don't know what. What else can you provide with that method?
Yeah, interesting question. I'm not sure right now in terms of kinetics or kinematics. The only thing right now I can provide is with the kinematics with the position data, and then perhaps something with, but yeah, I'm just not sure at this point.
You know, I have the feeling that a lot of these variable methods impose us what we have to measure. That is not a logical thing that we say, this is what you like to know, and here is the sensor that can do that. It's the opposite, that is say, here is the sensor that can do this and this and this, and use it.
Yeah, certainly. I mean, our labs are pretty incredible in the way that we can get all these variables, and we get to pick and choose, but we're kind of confined when using wearable technology because they're only getting a subset of these variables.
Thank you.
Thank you.
Pratham, actually, I have one more question for you because I'm not familiar with wearable technology yet. So you briefly mentioned that it could be used in for the athletes in the future, but would there be any like a specific idea you have to how it would help the athletes to improve, like, I don't know, their performance, or how it could contribute it?
Yeah, certainly. So like I mentioned, it's important to profile external load for athletes during match play and during practices. During practices, it's quite easy to have the athlete wear whatever sort of wearable technology and seeing how they perform in a controlled environment. But then when you go to match play, it is a little bit more difficult just because some leagues have rules that don't allow you to wear certain wearable technologies. Some athletes are super finicky when playing, that they don't want things being disrupted. So yeah, I think it'll just take a concerted effort by everyone just to make sure that athletes stay at peak performance while also not suffering any terrible injuries. Yeah.
Thank you. Walter, please go ahead.
Hey, Pratham, during the talk, I guess I was asking myself, because you stayed on a very technical level, and it didn't become clear to me in what kind of a context you did that work. And is it correct to assume then that this is essentially technical work where you try to evaluate this technology, or do you have a very specific application in mind where you try at the end of the day to solve a research problem for yourself?
So I think this is a very unique research problem, in that I am comparing a system to a gold standard, and if this system was, for lack of a better term, validated, it could then go on to seeing how runners perform in a controlled setting, such as practices, or for basketball players. Yeah, so but the first step is always seeing whether this particular system can be used. And then from there on, we can tackle other research problems, such as, does having a stride length of 3.5 meters, is that better than 2.5 meters, sort of thing with the system?
And when you did the testing, you said you did that in the laboratory setup with the camera set up for gold standard evaluation. Do you think that biased your results towards being better than they normally would be, because you're in a laboratory setup, you do straight walking and running, whereas you talk about basketball playing and soccer and this type of thing, it's outdoors, it's involves curving and running, and twisting and turning. Do you think you actually got best results possible for the system, and in reality it might not necessarily perform as well as you had it today?
Yeah, that's definitely one thing that I just couldn't get around, was testing in a confined laboratory where there's all these cameras and different systems that the participants just aren't used to. So looking towards the future, I would like to bring what I did in this setting to an outdoor setting, where perhaps the participants may be a little bit more comfortable. But I think for what I did, where the participants were recreationally active participants from the student community, this was probably a good first step.
The other thing that was very interesting was, you gave as an example that, if the system had a slight error, then you might potentially identify a talented soccer player, was the example that you gave. And many years ago, I was trained as a physical education teacher, and for about 25 or 30 years of my life, I I coached athletes, and I said once to people, or I said on many occasions, that give me a bunch of 7-year-old kids and put them to, like first graders, and put them into a gym with me. And at the end of the hour, I will tell you who of these kids will never ever be an Olympic champion in track and field. After 1 hour, 7-year-old kids. And of course, I don't know if that statement is correct because it's never really been scientifically proven. But the question really being, would coaches and do coaches and athletes really rely on that type of technology? If I wanted to see who is a good sprinter in soccer, I would have my 11 players line up on a line, give a shot and let them run to the middle of the field and have a 50-meter sprint or a 40-meter sprint, and I would see who crosses the line first, and I would know who's the fastest sprinter. So how accepted is that technology now, and how acceptable will it be in the future, or what needs to be done that it actually becomes accepted by athletes and coaches beyond what traditionally coaches and athletes do today?
Yeah, yeah, great questions. So the idea of just having kids run 50 meters and seeing who is the fastest, I think may not work because you may want to get the first 10, 20, 10-meter splits, so that even though you got someone who can run, perhaps they can't do other things, but someone who has very good 10 to 20, 20 to 30 meter splits, you can quantify that using wearable technology, and then work with them over a course of time. So then they become a better complete player. In terms of how the industry is evolving, well, I would say that they are getting more towards this towards data analytics, and seeing whether they can improve athletes or maintain their peak performance by quantifying many things, and getting away from just a coach's word saying, "Yep, he's good. My I saw that." Now there is value in that, but I don't think the industry has reached a symbiotic relationship between wearable technologies and data analytics and the word of a coach. I think there's still teams and organizations that are trying to find this balance. Whether we've reached it or not, in my personal opinion, I don't think we've reached it yet. But it is a lot better than, in my opinion, than what it was 30, 40 years ago.
Maybe just a last question, because you said that the LPS was provided to you by a company, if I understood correctly. When you have that situation where a company provides you with an instrument that you then essentially evaluate, did you feel there was a certain pressure on you or a certain uncomfortableness because you wanted the device to be good, or do you feel that you could work in a completely unbiased way? And
Yeah, I mean, I hope as a scientist that never happens to any of us, where we feel pressure from an outside source to do something, or fudge the results, as it may be, or feel that pressure to fudge the results.
No,
I
that
think,
and don't misunderstand me. I didn't want to imply anything like that at all. But I know for myself, you read an article and it says many things, and you like one thing, and that there's a certain bias of recognizing more what you like or what you like to see, kind of this. And I think we all have that unconsciously. I know I do, and I think most of us do that. You kind of tend to give more weight to things that seem to emphasize or reinforce what you're thinking compared to things that you might not quite agree with. And I think we all have that a bit, and I think we all have to fight that a bit as scientists on an everyday basis. And so I just wondered if that potentially might play a role, when I didn't want to imply anything about data fudging and that type of stuff, that's a given.
Yeah, no, I understand what you're saying now. Yeah, I mean, maybe on some unconscious level, I was experiencing that bias. It certainly wasn't intentional. I think being away from that company and being in an environment where the data speaks for itself here at the HPL reduced a lot of that bias, because I think if I were doing this exact same testing in Penticton, British Columbia, there may have been a little bit more pressure from the company. But being in this environment where I'm away from that, I think to the best of my abilities, I was unbiased.
Yeah, good. Thanks.
Okay, I see, Philip, you have a question if you are around?
Yeah. So earlier in the discussion, Pratham, you mentioned, if I understood it correctly, that the signal that get picked up by the local coordinates or local system is more variable.
Yes.
So then if you move further away from it, especially with respect to your data, if you had a chance to look into it to see whether the further away the people walk or run, does the data get more accurate when you just look into those specific steps, like just the last final steps, for instance?
Sure, yeah. So this system could pick up the sensor up to 100 meters. But looking at my data a little bit more closely, there were quite a few trials that showed a little bit of a wobble in the signals as they got closer to that, that 10 meter mark. Yeah, moving forward, perhaps the system could perform better during that first step or that first stride. But the problem with that was that the participants wouldn't have been reaching a steady state. So that's why I stuck with the 10 meter, like the last stride before that 10 meter mark. So that's why I want to explore, okay, maybe getting the instantaneous speed is quite variable, but maybe getting the average speed is a little bit less variable, and you don't worry about those wobbles as much.
Okay, then I have another question, or maybe two in a row. So one point would be, is it potentially an unfair comparison if you compare 8 cameras against one sensor sending out some data or some information and receiving information? And then is it also possible to link several of those sensors together to potentially increase the accuracy?
Yeah, so to your first question, I absolutely agree that perhaps increasing the number of LPS hubs we could get a more accurate picture. But we also want to be wary that we don't increase it too much so that we take valuable time away from the athlete, because ultimately this product needs to be marketed appropriately. What that number is, I'm not sure, but it would be interesting to look at eight hubs versus 8 MOCAP cameras. Yeah, that could be interesting. And then to your second, sorry, what was your second question again?
I mean, it's kind of the same question, more or less. You kind of answered it. It was like, okay, is there some research out there that basically has tested 2 of those LPS systems linked to each other? Or
right. So actually, the company that I'm working with, they are exploring having 2 sensors on the same participant. So like I had mentioned earlier, when the participant turns around and the sensor is no longer in view, the signal gets scrambled just because humans being liquid materials, the signal can't penetrate humans. So they've put a sensor on the front as well. So when you turn around, you can get the position of the person in that condition as well. So they have looked at tying together multiple sensors to a single hub. But yeah, personally, I think they should be exploring testing multiple hubs, but to a certain number. What that number is, I don't know.
okay, thank you.
Thank you.
Okay, I think I see Brent raising your hand. Please go ahead.
Pratham, my question is about the Bland-Altman plots and how to interpret one of the numbers that you were reporting. So you report the limits of agreement, which are defined as 1.96 times the standard deviation. And then, and so basically what that comes down from is like from a 95% confidence interval. And so if you have a perfectly normal distribution, 95% of the data are going to be within 1.96 standard deviations of it. So you report that number, but then you report this number of points outside of limits of agreement. And
Right.
if it's a perfectly normal distribution, it has to be 5%. And I noticed that it was always between like 3 and 6%. Like it didn't really change that much. So I'm just wondering if is that an important metric to actually report? And if so, it seems to me like all it really does is communicate how normal the distribution actually is. Because I would think if it's not close to 5%, then it's probably not a normal distribution. It's just some other kind of distribution.
Sure. Yeah. By me reporting that, I was just saying that the limits of agreement were within the data points were within those limits of agreements, and it was 95% confidence. And even though that number was low, what we really should be looking at is the variability, either the difference in the limits of agreement or the range of the data points.
Yeah, okay, that makes sense. Because in my mind, you could have a really great fit and you could have a really poor fit. And 5% of the data points are always going to lie outside of the limits of agreement if it's a normal distribution.
Exactly, if it's a normal distribution. I just want to show that it was a normal distribution. Yeah.
Okay. All right. Thanks.
Would there be any last or final question to Pratham? Oh yeah, Walter, please go ahead.
I just have a last quick question, and that is, if I understood correctly, then you detect and you independently measure from that system the stride lengths and the stride frequency and the speed, but the three are obviously connected. And I wonder, if you now take two of the three and you calculate the third, do you actually get the same result as your independent measurements suggest? So for example, if you take the stride lengths that you get independently, stride frequency, and then calculate from that a speed, do you actually get the speed that you also measure, in an independent manner? So is it internally consistent in that manner?
Yeah, I haven't explored that, but it would be interesting to see if they match up, because theoretically they should, right?
Good, thanks.
Yeah, I think I saw Benno, you raising your hand. Please go ahead.
So for your master's thesis, is that the topic, or do you have a different topic?
No, this is my topic.
This is the topic, okay.
Yes.
Thank you.
Okay, if there is any last final comments or question. Okay, I do not see anyone raising your hand. I would like to thank Pratham again for sharing his thesis work. For the next week's seminar, there is a small change from what we have on our website. We'll be hearing from Dr. Eng-Kwan Mu, who will be talking about sarcomere length non-uniformity in single myofibrils and entire muscles. I'll see you all next week.